In the transrectal or transvaginal probe, there are different probes, but the idea is that I have the elements present. The elements, as we can see, are arranged in this way inside the transducer. If we look here, we will find that they have height and at the same time have width in this direction. The height or elevation determines something called slide thickness, which is referred to as the elevation plane. Now this width, it's about what I call the probe itself, okay? What I refer to. What about this? This determines your field of view. In linear, it gives you a rectangular field of view, and in curved, linear, or convex, it provides a field of view that increases with depth. Each element is connected by a wire, and this wire gives you an electrical signal or electrical shock that creates the vibration for the piezoelectric material. In the matching layer, which comes after the piezoelectric material, its thickness is a quarter of the wavelength, meaning 1/4 of the ultrasound pulse wavelength you want. Why? Because if there is a reflection of the ultrasound beam, the reflected ultrasound pulse that comes back is what you want to create destructive interference for. It is said that in this matching layer, if there is a wave traveling through it and it is a quarter of the wavelength, in this case, you are in phase or out of phase with the reflected beam coming from the patient. In this case, it creates destructive interference and prevents it from reaching the crystal again. The matching layer has an impedance that is between the soft tissue and the impedance of your piezoelectric material. Now, these are the different types of probes. I have the linear, the curved, or convex, and the sector. The same field of view applies here. Of course, you know it better than I do. The focusing process that occurs in the linear or convex probes, as I explained, is somewhat different in the sector or phased array. In the sector or phased array, you have a small window like this. Notice here, these are the different electrical pulses. These electrical pulses, 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 electrical. It's like you're taking a certain large field of view, but moving, for example, from side to side. How does this happen? You are focusing here and then moving from this direction to that direction. How does this happen? This occurs because you want to set your focus point in this area, so you create a delay. You take the semicircle we were talking about, so here is the semicircle, or here is the circle, I apologize, and here is your circle. This distance is this, and this distance is that, and this distance is this, and so on. This distance calculates the delay time that we are all talking about. And this time is what you use to send the signal to this element, number 1, then 2, then 3, then 4, and so on, until you reach the element that is already on the surface of your circle. The interference that will occur will be more focused on the focal points you want to capture, which are the beginning of your field of view. Then you move to the next point, 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 move to the next point. Do you see where all the interference is concentrated? In this area. These are the focal points that you want to establish as the beginning of your field view, and you intend to move as if you are taking a scan. This is in the face of the array or in the sector where you are working on cardiac tasks. Here is the view, and here is the different signals. See which one will activate. This is the transmission or the first focus point. Also, when you come to do the receiving, you will do the same thing. You will create an electronic circuit that will adjust the delay in time to synchronize all signals arriving at the same timing. This is the face of the array and the beam focusing that takes place. You have multiple focal zones. First focal zone, second focal zone, third focal zone, and so on. What happening here is the constructive interference occurring in the near field area. This is what happens with destructive interference. As you can see, the two pulses here move at the same time, meaning both are moving simultaneously. The running and the blocking are both together at the same time, but out of phase means that the signal at the top is opposed by the bottom, and the bottom is opposed by the top. Therefore, the two signals cancel each other out, resulting in a weak output like this, unlike in constructive interference, which is the constructive overlap between the ultrasound pulses. All right, we are good with that. We talked about the ultrasound transducer and the focusing that occurs with different signals. This is the same information. It seems like it is changing the timing between the elements and the signals. You can see that as you change your focal angle or your focal points, it starts to alter the timing of the electrical signal that activates the existing elements. The shape of the beam that comes out has resolution aspects. I have an ultrasound transducer, as I mentioned, which is arranged in this way. There is elevation here or height. This height represents the elevation plan, which is the thickness of your slide, the thickness you are taking. Your frame thickness is how much, and there is a part related to axial resolution, which is how you separate two objects if you want to distinguish between them. Axial resolution depends on frequency and pulse length. As for lateral resolution, it depends on line density, how many lines are present, and the width of the beam. The width of the beam is one of the two important parameters, along with axial resolution and retro resolution, and their significance in image quality. The typical value of your axial resolution depends on pulse length. Lateral resolution depends on beam width. Axial resolution is 0.2, 0.5 mm, lateral 2 to 5 mm. Higher frequency improves resolution. Approximately 2.5 millimeters for axial and in the range of 3.8 millimeters for lateral. Improving the processed future regarding slide thickness is a hot topic for enhancement of the array. Slide thickness is one of those things that is supposed to be related to the array of elements, which is called 1.5D. It has a special array or special configuration that exists. Is it hers? Are you there? Regarding the elements present on the ultrasound transducer, there is a mention of 1.5D elements, elevation, and improvements in the topic of frame thickness or image thickness, which I consider to be under research. There is work being done to improve the topic of fly thickness in ultrasound imaging. Design technique or design technology is considered under design specification. In this context, there is work on improving the subject of design techniques regarding design. For the Vizdari, We have discussed the topic of resolution and axial resolution, the relationship of axial resolution with pulse length, and the relationship of lateral resolution with beam width. It is expected that the highest lateral resolution will be in the focal zone. Better. And of course, this should be in this area, the highest area in the As an example, here it demonstrates to you the shape of the image in the near field, focal, and far field areas concerning thickness resolution, elevation plan, and lateral resolution, and provides a clear understanding of these aspects. There is something, contrast resolution. We have taken contrast resolution in the topic of ST. What is contrast resolution? Can someone remind me what contrast resolution means in the context of the topic? Sorry, Dr. Basma, but this is the contrast. If I say that I have a certain object and I want to distinguish it from the background, that is contrast, or the concept of contrast. But if you remember, for example, I was talking about having lesions in the liver, right? If I have a stone in the kidney, is this stone high density or low density? High density, and the kidney has a significant difference in density between these two objects, right or wrong. In this case, I deal with this object and say I want to measure the image quality. I talk about contrast, about the contrast between something high density and something low density. Okay? If I have lesions, for example, things like lipomas, if I have a lesion with no density difference between it and the background, there is a significant difference. For example, there are focal lesions in the liver. If I have a lipoma case, there are things that will be better than others. The resolution between it and the background is not very strong, or you need to slightly adjust the window to measure the house, field, unit. I call this contrast resolution, which is the machine's ability to enhance the contrast between the lesion and the background. Is that clear? Okay. Is this understood as a concept? Okay. If we talk about the same thing, for example, you have some differences between it and what surrounds it. This difference is the machine's ability to process or see it well. In this case, you have improved the contrast resolution, meaning you have enhanced the detail resolution, allowing you to see at a higher level or with finer details. We said that this topic depends on the shades of gray. I mentioned that for each pixel, I assign a number of bits. I hope you remember this information. The bits I mentioned are the signal I receive, which I convert into what is called digital form or digitalization, representing it in zeros and ones. Each pixel has a certain number of bits, and the bit, which is the single bit, is either 0 or 1. So, I am saying, for example, how many gray values I can place within the pixel. The more the number of bits I have, any image in the world is made up of pixels, and each pixel is a square. For me, each pixel contains information, and this information is stored in bits. The more bits present in a pixel, the greater the number of signal values or gray values that can be stored in that pixel. For example, if you remember in Al-Ashat As-Siniya, I mentioned that in this image, the bits in one pixel are 1, in another pixel they are 4, and in another pixel they are 8. I would say 2 to the power of 1 gives you the number of gray values or shades of gray you can take. This initial image only had 2 gray values, black or white. For 4 bits, 4 to the power of 2 gives you 16 gray values. For 8 bits, it would be 8 to the power of 2. Each pixel can take 256 values, allowing for significant differentiation. The same idea exists in an ultrasound, but instead of discussing CT numbers, we talk about something called a decibel. It's as if the pixel is receiving a certain intensity of reflection, which is represented in decibel. So how many decibel can a pixel accommodate? If the decibel is, for example, 40, the image will look like this. But at 80 decibel, the image improves. The gray values or the values you have are now higher, allowing you to achieve a better image and identify the problem. This concept applies to all imaging modalities and relates to the dynamic range or the bits number present in the pixel. For example, in an image like this with poor contrast resolution, you only see 2 colors, black and white. As for this image, I can see all the gray values. So the quality, contrast, and resolution depend on the number of bits. If the number of bits increases, it enhances the image. 1024 bytes is the size of the pixel, the size of the image, the size of your picture. The larger your number increases, the better it is for you, but it comes at the expense of. This is because the more pixels you have, the more detail and clarity your image will possess. However, keep in mind that larger file sizes may require more storage space and processing power. This is what I call dynamic range. Here we talk about the topic of resolution and different frequencies. The low frequency from 3 to 5 MHz is used because it is a lower frequency, so the attenuation will be less, allowing it to reach deeper abdominal organs such as the liver, gallbladder, and kidneys. A frequency range of 3 to 5 MHz is used because it is a low frequency, which means its attenuation will be lower, allowing it to reach deeper abdominal organs like the liver, gallbladder, and kidneys. High-frequency probes, 10-15 MHz, are for superficial use, offering high resolution but limited penetration. Mid-frequency, 4 to 7 MHz, reaches deeper. What do you want? But your device will be for 3 to 4 centimeters. The frequency range of 4 to 7 MHz allows you to reach deeper structures at about 10-15, like for example the brachial plexus, located in the infraclavicular region, right? And the sciatic nerve. So according to the frequency, you can achieve a certain resolution and obtain a specific depth. The multifocal approach helps you with resolution and adjustment. Instead of having just one focal zone, you now have different focal zones. Yes, it is possible for the system to hang before the machine, of course, if your hardware is not compatible with this technology. In certain situations, it is indeed a possibility that the system might experience a hang-up or freeze prior to the machine itself, especially in scenarios where your hardware components are not fully compatible with the latest advancements in this technology. Thus, X resolution depends on special pulse length, while lateral resolution depends on beam width. The third type of resolution, contrast resolution, is based on the number of bits present in the pixel, which I refer to as dynamic range. So this is the contrast resolution, and this is the lateral resolution. This is the fourth type of resolution, which is, in essence, temporal resolution. Temporal means something related to time, in a way that something moves over time, and you want to accurately detect its motion. For instance, without any unwanted artifacts and with the appropriate level of resolution, such as, for example, So, in what cases is temporal resolution important in various fields and applications? Hi there.